Hey, John here. Let's talk about performing I/O to files inside C++. Now, fortunately, we are already quite familiar with writing to files and reading from them, because if you print a message to standard out, or in C++, C out, they would call it, the messages in the insertion operator, this guy right here, are writing to files. C out is an output file stream, okay? And C in is an input file stream. So you actually already know how to at least deal with exchanging text with files. Now, if you want to open your own file in addition to the keyboard and the screen and your terminal, right? You can use you can create an instance of an Ifstream object. That's defined in this header file up here, the fstream include that defines fstream, ifstream, and ofstream. Obviously, this is the input files. These are output files. And you can use this generalized fstream to actually open files and do both reading and writing in the same file. And we'll get to that a little bit later. For now, let's just open up a file and read from it, okay? So you're going to create an instance of ifstream. I'm going to call mine in1, and then I'm going to call in1.open. To open it, I have to give it a file name, okay? Normally, you would never hard code a file name in a program. It is really kind of pointless to do that. You'd want to pass this in as an argument somehow. But for demonstration purposes, it doesn't really matter how it gets into the code. To keep this simple and focused, I'm going to just hard code it in here. So tf1 test file 1-in.text is my name of my test file. I'm going to create a string object. And I'm going to use it the same way I would from like C in. But in this case, I'm going to just open, or I'm going to use rather the object I created, I opened up here. In one extraction operator string, it says read a string from that file. Then I'm going to say got, and then in single quotes, I'm going to print out what I read in. When I'm done with it, I want to close it. It turns out because this is a local variable, and it is an object, and it will be destructed when it goes out of scope and leaves these curly brackets here. The close will automatically get called for me in the destructor of this object. So in some cases, you don't really have to close these. But for to be formally correct and proper, I'm explicitly closing it here before I return from the function. So, all right, so let's go ahead and compile it and run it and see. Well, I guess let's first look at my test file, right? Here's a bunch of files in this directory. Here's my test file 1.txt. It's filled with a bunch of words from lorem ipsum. If you don't know what that is, Google it. Let's go ahead and run the program now. Prog1, it's going to open that file and then just print out the strings it gets out of there. So it goes pretty fast, and it scrolls up the screen. There we go. Because here's me running the program. It says I got lorem, I got ipsum, I got dollar, and you can see these are obviously the single strings, the tokens that it reads in, and amit, comma, like that, because there's no space after it. That's what a string does. It reads all characters that are separated by white spaces, okay? So we get all of the words out of that file. Now, normally you wouldn't want to just open a file and assume all is well. Okay, so here's how you check to see if the open worked. This time I'm going to put the file name itself into a string variable so that I can use it here in my open instead of explicitly hard coding a string in there, and then reuse it later if I have an error in the error message, because it is of zero value to any user to print a message that says I can't open some file without bothering to tell the user what it is that could not be opened. Okay, so what is this going to do? It's going to open a file. If the file does not succeed for some reason, it will be in a failed state, and this method will return true. I then print this message to see error. All right, now see error is a lot like standard out, but this is what we call standard error. Errors can be written to a separate place than the standard output goes. Quite often, they're both going to the same place. If you don't do anything at all and you just run this thing on the shell, they both output standard out and standard error go to the same place. However, if you redirect the output of a program into a file or into a pipe or something like that, and you have something that needs to be printed to the user, you don't want that to go into the data that's been redirected Okay, so this will end up going to the terminal even though the output of the program might be saved in a file or something like that. This allows your users to see error messages, all right? Now, you don't use this lightly. I only use it myself in a case of a critical error if I'm going to abort the program or something like this, all right? These are fatal errors generally go to see error. Very rarely do you use it for, or should you use it for anything else, at least in my opinion, all right? So what's going on here? I open the file, I ask, did it work? If it did not work, it's in a failed state. I print a message that says I can't open my file. I terminate the program manually, explicitly. I forcibly terminate it right here. And after that, you've already seen the code over here. All right, it's already compiled. Let's go ahead and run probe 1A. And you can see, hi, I can't open this file xxx.txt because there isn't one. If I wanted, if I wanted to, I could copy the ipsum lorem, or I could just create one here like this and put, blah, 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 1, 2, 3, 4, 5, and say hello, like so. Rerun that program. And this time it can open the file, and therefore it does open it, and we go on our merry way, and it does the same thing the last program did. Let me go ahead and remove it, because I don't want that garbage file in there anymore. That was just for demonstration. All right, so let's see what happens in program 2. This time we're going to create an OF stream instead of an IF stream. All right, well, we're going to do the same thing. I'm going to create a variable called file name, or f name in this case. I'm going to create a file called tf2out.txt, and I'm going to open it. Now, if I don't tell it any other parameters or anything in here, by default, if I just say open and it's an output file, it's either going to create a new file if there is not one already there, or if there is one already there, it will delete all of its contents, clear it out, and I will then be writing into the file. So this will clobber the contents of this file if it exists, okay? Again, I can ask, did it work? Was I able to open that file? All right, maybe I couldn't, open it for writing or something. It could be an error of some kind. Just like an input file, I write an error message, a standard error, and I include the file name so that it makes sense when I say I cannot create or open a file. I tell the user what the file is I'm trying to create, and then I go into a loop down here. What do? I'm reading from standard in. And I print to standard out, hi, I got this string. And then I write into my output file that I opened up here the exact same message, but I use angle brackets instead of quotes, just so we don't get disoriented when we look at either one of these outputs. And then when I'm done, I want to close it. And when you're writing data to output files like this, especially when you're using high-level constructs like, an OF stream, the data that's going into the file is buffered by the library functions in your application, okay? If you don't close it before your program exits, you could lose an arbitrarily large amount of data that you wrote to that file because it didn't get flushed. You need to make sure these are closed, okay? Especially when you're writing to them. Now, again, because this is a local variable, it'll go out of scope, and the destructor of an output file stream will close it for you. So whether I do this or not, I happen to know this particular program, it will work, just like I said about the input. But you don't want to be sloppy about these things. If you're sloppy about this, you're probably sloppy about other things, and your program will have problems. Don't do things esoteric. All right? Don't be esoteric about what you're doing. So let's go ahead and run this one. But I guess before we run it, note that we do have this text file here. So let's run it in a couple of different times because we want to see all the different combinations of what's happening here. So this is test file 2 out.txt, which is going to be created. Now remember, it'll be truncated and then filled in because it already exists, right? So let's go ahead and run this once, and remember, and it's going to read words from standard in when it goes. So it's waiting for me to type in these things that it wants to receive. So I'm going to put 99999, and then I'm going to put AAAAA or ZAAA or whatever the heck it is I'm typing here. And then I'm going to hit Control D to say end of file on standard in, and the program will get EOF and it will stop. Now let's look and see what's happening here. So TF2 out.txt, this 66 right there is the exact number of bytes that are in this file. This was before I ran my program. So if I list ls, this is short for ls minus l, like that, by the way. I can see the 66 bytes changed to 28. So I know something happened, and the file became smaller. So it probably worked right. You can see the 9s and the ZAAA and so on, all right? So this thing created this file. It didn't create it because it was already there. It truncated its contents, and then it wrote the data that I typed in into it as the program was supposed to. So let's go ahead and remove this file now and run the program again. Go back in my history here. Here we go, Prog 2. So now it will have created it because it didn't exist at all. And let's go 444444 and D and G or whatever I'm going to do. Control D to hit the end of file and look and see what's happening here. It created a new file and filled it in with this new data. Now let's see an example of what happens when you cannot open a file. If I change the permission modes of this file, if you don't know what this stuff over here means, the short of it is it tells you who's allowed to open that file and read from it and write to it. If you say change mod 0 and you give it a file that exists, these permissions all go away. No, the R's and W's have to do with reading and writing. This is me, the owner of the file, gets these 3 letters. It's or rather these 3 here. It's read, write, and execute permissions. The group that I'm a member of is this these permissions here, and this is everyone else on the Unix system. What their permissions are. So myself and my group can read and write the file, and others can read it, but they're not allowed to modify it. Now this down here is the file in question. This says no one's allowed to read or write that file. All right, so if I run the program again now, it should fail because it cannot open it for anything, and it certainly can't write to it to truncate its contents, and we can see it can't do that. Now this error message is probably not optimal because it's not worried about creating it per se. I might want to rephrase that if this was a professional application, all right? You can see that the file is still there, and because I can't open it, I can't open it. No one can. You have to change the permissions back again. And the permissions that it used to be set to were that. You can go look around, change mod. There's some plenty of websites that'll explain how that works. It's a subject of a different lecture, and you can see the old data is still in there. All right, so what's in prog3.cc now? If you come down here and look, now I'm saying open, and I'm giving it an extra parameter over here. It's the exact same program that we just played with, but I've added this one thing over here, standard IOStream app, which stands for append. So I threw in a comment over here. Open a new stream or open a new or existing file, and I want to be appending to the end of it. Okay, so this means if it does not exist, it'll create a new empty file, and then I'll be writing into that new empty file. If the file does already exist, app won't truncate its contents. It won't clear it out. What it'll do is it'll leave everything in there alone, and it will set up this variable here, or rather the out1 object, so that when I write to it down here, all the data I write to it will go on the end of the file. It will be appended to what is already in that file. So if we run that, okay, it's already compiled. If we look at what's in TF2 out, this is the file that it opens, right? And you see the 444 DDD and GGG in there, right? So if I run now prog3, it didn't complain, so it obviously could open it. And let's put in what? KKKKKKK and whatever, SSSSSS and whatever, A, B, C, D, E, F, G. Okay, and then I'm going to hit Control D to end that file. ls-l, and you can see the file here grew in size. It was 41, now it's 145, so I wrote a few more bytes into it. And you can see them in there. There's the K's, S's, and the A, B, C, D, F, G. All right, so there's appending to a file. Let's make sure that we have a shared set of terminology when we're talking about files as we move forward here. So a file in C++ is an array of characters, okay? So let's say we have a file and it has an A, B, C, D, E, F, G in it, and maybe there's a carriage return at the end of the line, an EOL in there, okay? So let's say this is the contents of my file. The size of the file is given by as the number of bytes in this file, right? 1, 2, 3, 4, 5, 6, 7, 8 in this case. So my size, if this is in that file, it is equal to 8. The position of the first byte in the file, which we call the beginning, abbreviated BEG, equals 0. Okay? The position of the byte at the end of the file would, by definition, be size minus 1. This is basically a byte array that's stored on disk. And I'm going to put a box around this \n here. All right? That is a single character, not 2 characters. All right, this is how we notate a carriage return or the end of line, right? So \n in single quotes is this one character representation of ENDL. At least that's true on Unix systems. It's not always true on Windows. And L is a 2-byte sequence on a Windows system. But we're focusing right now on Linux, which is Unix compatible. So this is what it represents on Unix. In Hex, we'll see this as a 0A, okay, is the encoded value of this new line character. So you'll see the A, B, C, D, E, F, G, and then a numeric value if you print it out in Hex, which would be 0A for the end of line. All right, so these are the terminology that we use when we're talking about files. Now, why do we need to talk about these terminology? This notion of position, right? When we have a file on a disk and you're writing data into it, what you're doing is you're moving this position. The current position is set to the end of the file. So if I have the contents of a file, I've written this line into it, like they say, oops. If I say something like, output file, double left, and I just put like that, A, B, C, D, E, F, G, \n, like this, then that's what will be in the file right now, and the size would be accordingly, right? 5, 6, 7, is that right? A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, 8, right? Of course, I already calculated it. It's early. Forgive me. Okay, so if I then wrote OF is then insert 1, 2, 3, and I don't put an end of line on there, then what happens is this 1, 2, and 3 will be concatenated to the end of this, a 1, 2, and a 3. Okay, at which point the size will grow by 3 characters. Okay, now size would equal 11. Okay, and it would reach to the end of this whole thing. The point of all this is that this position there's a notation of a get position and a put position. All right, so every time I put something into this file, I'm moving over this put position pointer. It keeps moving over to the point at the byte, the first byte that is after the full contents of the file right now. And so right now, after I've done this, that position pointer would be right there, and it would equal 11. 11 is the number, the index number of the first non-existent byte at the end of that file. So OF, I put an X in there. Then the X would show up here because that's where the put position currently was pointing. And the put position is then moved over because I just filled it with this, and this keeps on going. All right. Now, the point of all this put and get stuff is if I wanted to, at this point in my code, I could tell the C++ environment to move this pointer back over here. Or wherever I want, quite frankly. So if I did that, I could say something like output file dot seek p. I'm going to seek around in the file, all right? And I can give it a position in here. And when I do this, I can say move it back, say 1, 2, 3, 4, 5, 6, 7. I could say move it to -7 from the current position. I can say move it to negative maybe 1, 2, 3 from the end of the file. And I can move it to position like 0, 1, 2 from the beginning of the file. All right. So I have these three different references, the vantage points, what is referred to as the whence. Okay. I can say beginning, I can say current, and I can say end. It's a terrible looking end. Let me just etch that off. End. Okay. So this is the positions relative to these three places where I am now from the beginning of the file and from the end of the file. So 0 from the beginning is the first character. 0 from the end is the end of the file. In this case, it would be over here. And 0 from current doesn't move it at all. Okay, so if I wanted to, I could move it, say, back. I could say, -4 from the current position. And I'd be pointing at this 1 right here. And then if I said output file, insert, ZZZ, what that would do, right? If I moved it to -4, so that would be what? Seek P, output file, seek P dot, or rather, no dot there. The dot goes over here. -4 from... Oh my gosh, I'm out of margins here. Give me some more room. So after this one here, or in lieu of this one here, what I'm saying is output file dot seek P, maybe -4 from the current position. Right, at this point it would be here. So we go 1, 2, 3, 4 in the negative direction. I then said something like output file dot, or rather, insert ZZZ. What would happen is it would replace the 1, 2, 3 with the ZZZ. It would leave the current position pointing at the X, not the end of the file. The X would still be in that file. Okay, it would only replace the 3 characters at the current pointer, at the current position, which we just moved back by 4 right here. Okay, so let's code this up and make sure this works before we get any fancier. All right, so this should all look pretty familiar. We're opening an output file stream. Okay, in this manner it will create and or truncate that output file. We check to make sure it worked okay. Here's the code that I said let's try. Okay, now I added one other line. There's, along with seek P, there's tell P. This is tell me where I am right now. Okay, so what am I doing here? I'm saying here, there's a little message, tell P equals, and I'm going to be able to print out, here's the current position before I modify it. There's a little debug output here, right? And after I've modified it, I can ask it again. Now, where am I, right? Now, well, this one down here, it better be for less than the current position. And that's how you specify, I want to move relative to the current position in the file. Okay? Here's me rewriting ZZZ into the file here, all right? So let's go ahead and clean up. I just ran a test of this before I started recording, so let's clear up all this stuff here, make the file, and let's run it now. Okay, so this is the one we were just looking at. So here's my tell P. It was at 12, and it backed up to 8, which matches our hand drawing perfectly. Luckily for us, there's the file that we created, right? It was not there here because I removed it. Now it miraculously appeared because we ran our program. It still has 12 bytes in it. All this is overwhelmingly good news, right? Because after we moved, we wrote more data into it. If we didn't move it back, this would have been bigger by whatever, 3 bytes, right? So we can say cat this thing and we can see what's going on. Now we have to look very closely at this because after the X in the file, there was no new line at the end of the file, but there's our Z's. And it overwrote, presumably, the 1, 2, 3 that was in there. Now, there's a lot of hand waving in here. This can be real easy to fool yourself on. So let's make sure that this is doing exactly what we think it's doing before we move on. Let's hex dump minus big C. I've shown this before in other videos. If this is your first time, what it is it says, show me the hexadecimal codes for every single byte, one at a time, of the given file over here. And the capital C means in the canonical format. Why the canonical format is not the default, I do not know. But the default looks like this, which is very annoying, okay? So the canonical format, which is what you pretty much see everywhere on the planet, other than for some reason the default that somebody decided to use here. Now, what do you see in the canonical that you don't see in the default? Well, you'll notice that in the default, these are out of order. Look at this, 62, 61, and this is 61, 62. Just don't use this, all right? Unless you know exactly what you're doing, use Hex Dump minus big C, 1 byte at a time, and print them out in order. Thank you very much. Don't help me. The other thing that's different is, over on the right here, you see the ASCII printable character glyphs that each one of these bytes over here represents. 1 at a time in the same order, and they match. This little dot here is printed whenever there's a character over here, a byte value, I should say, over here, that does not have anything that could be printed in a, in a sane way in a list like this. That OA is the end of line variable in C++, or the carriage return. This is the new line, actually. I misspoke. OA is technically a new line character, which represents the end of the line on Unix systems, okay? So that's what Hex Dump is doing. It lets us see our file in both hex and printable ASCII. And this matches exactly our hand sketch, all right? Now, if we go back to our program here, now let's make sure it's doing what we wanted it to do. I'm going to leave the tel p in there. And I'm going to comment this stuff out. I'm not going to seek. I'm not going to overwrite anything, because we need to know that it actually started where we wanted it to. If I run this program now, I should see A, B, C, D, E, F, G, a carriage return, or a new line rather. Boy, I can't get off of saying this wrong. I apologize. \n means new line, which is different than a carriage return. So we're going to see A, B, C, D, E, F, G, a new line, a 1, 2, 3, and an X. The 1, 2, 3 will not be overwritten down here, okay? So if we compile this and run that, and we rerun our Hex Dump, and we see the 1, 2, 3 in there. So this is pretty good evidence that we did write a 1, 2, 3 in there, and that we really did back up, and we rewrote the ZZZs on top of the 1, 2, 3. Okay, because if I don't back up and rewrite it, we can see what was there before. All right, so now let's make a massive leap forward here. Now, some of this stuff is really not obvious, all right? This is hard to figure out. How do you open a file so that you can write into it without clobbering it? Well, what you do is this, like I said, it makes me wonder if I'm doing this wrong. Feel free to put a comment below. What I've got here is an output file stream, okay? And I'm telling it to open it for input and output, which actually makes no sense. You cannot do input on an output file stream. This might be a great job interview question. If you ever go someplace, you get a huge ego, some guy with a big ego in the room, ask him, how do I open an output file stream so that I don't have to clobber its contents? Either, you're not truncating it if it already exists. And this is the answer to that question. You open it and you specify you want to do input and output at the same time. Turns out it won't let you do the input, like I said, but it will open the file and not clobber it. So we check it for failure. That's just copied from the previous code. We got our usual strings. We can play games, reading from standard in. And what am I doing here? I'm going to say seek to the end of the file. All right. Now, if I don't do that, it's not clear where I really am. Okay. I open this file for output mode. Where am I? Well, I could open it and put myself in append mode if I wanted. We'll play games with this in a little bit later, all right? But for now, let's start with what works and then mess it up later. So what are we doing? We're opening it for output. I happen to know that the position of the stream will be at the beginning of the stream if we don't move it somewhere. So I'm going to say seek the put position, the position for writing into the file, to go to 0 bytes from the end of the file. I have no idea where it is right now. Doesn't matter to me. Just go to the end of the file. That's how you do that. I read a string from standard in, and I'm going to play my usual guy. Hey, I got this. I'm going to print it out on the screen. And while I'm doing that, I'm going to print also the current position in the file where I am. Then I'm going to say, if I'm not already, if I'm at the very beginning of the file, I don't want to go backwards because I can't, right? I'll end up with an error if I do that. So if I'm in the middle of the file somewhere, I'm going to back up 4 bytes to clobber the previous ending of the line. So it's a carriage return and the 3 characters after this thingy here, all right? So I am going to back up to this less than sign of the previous time I went through this loop, or whatever happens to be in the file when I first start running this. Now, this has actually got a little bit of a weird bug in it. Let's go like this, okay? Oops. If it's greater than 3 is the only time I can really back up 4, okay? So I just fixed a little weirdness in there. It turns out in this example, I never write less than 4 bytes into it anyway, but I don't want to give you an example of crappy code. I can't stand it when we do that. Okay, so here's my program. Here's a bunch of files. Let's start out by removing this test file. All right, and remember here, let me cat this guy out here. That's the name of the file that we're going to open. Okay, now let's see what happens here. If we run this program, well, let's compile it, make sure it's compiled, and we run it. First thing it says, I can't open it for writing. That's interesting. Why not? Well, I can't do that because of how I opened it here. If I just simply said open it for output, it'd work fine, as it would, create it or truncate it. But because I did this, I can't, it won't create the file. It will only open an existing file. So in order to run this particular example program, what I need to do is have one that's already there. So let's go back up here, grab the file name, and type touch in the file name. All right, what does that do? Well, there wasn't one up here, and now there is one down here. What I've done is touched that file. There's 2 reasons you touch a file. You touch a file, it does not exist, it creates the file. The creation time and the last update time is set to now. If I touch that file again and list it up, notice that the touch time, the last modified time, has changed. Okay? It's 2 reasons you would ever want to touch a file. Why you'd want to do it? I'll leave that as a task for the reader. But if you ever need to update the timestamp on a file, you now know how to do it. Okay, so let's run our program here with no existing data. Let's just put a bunch of text in there. A bunch of text in there. Now, the first one makes sense. It's going to go in at 0. And remember, that's why we put that special if case in there, to make sure that we don't back up beyond the beginning of that line. So if I put 3 lines of data, 3 strings in there, I should say, give it an end of file, and then we cat this thing out. So let's see here. First of all, look at its size. It grew from 0 to 48. We have a look-see at the file, and that is what we expect. Every time we wrote a line into the file, we wrote got, greater than, a string, less than, and then we wrote XYZ and a carriage return. And if we write another one in there, we would back up and write over the XYZ and the carriage return, and we go again and again and again. Finally, the last one that we did not back up on is still there. The XYZ and the carriage return are printed. That is what causes the prompt to come down here. And again, I just said carriage return, and I meant to say new line. I keep saying carriage return because different systems work different ways. I grew up on a different kind of a system. Anyway, this end of line here is the new line character, and these 3 characters here are what kept getting backed up by 4. Okay, now, that file already exists. It's already got data in it. Let's run our program again. If we run our program again, remember, it's going to seek to the end of the current file, and then it'll go into that loop where it backs up 4 and writes, backs up 4 and writes. So what should happen is this would disappear, and any new lines will be in there. So it'll just still be one giant line of text in there. Let's just say 1, 2, 3, 4, 5, right? So that'll add 5 more of these things to that file. End of file, cat, the file back out again, and sure enough, there's got 1, got 2, got 3, and you can see the XYZ up here was overwritten as we went along. Let's go ahead and run our hex dump, because again, never trust your eyes to what you see on the screen up here. There can always be some junk in there. You need to do this. You need to go back and say, hey, did it work perfectly? Are there no other secret characters in there that are broken? And let's now break our application and show you why that's true. Let's say you make a mistake in here and you seek to +4 instead of -4. What does that mean? We start out at the end of the file. We're saying, okay, I'm writing my stuff. I get something from the command line. I got a string. And then I seek to 4 beyond the end of the file. Because the current position, by definition up here, it is the end of the file. What's it going to do? Is that an error? Is it going to run? This is a great quiz question someday. No, it's not going to die. It's going to work perfectly. And it's going to do exactly what you said. So I just did 1 through 9 with a 0 in there. Now I'm going to just put a bunch of Z's, then I put a bunch of A's, then I put a bunch of Q's, all right? And I never deleted the file, so this file that is dumped up here is what we started with, exactly, all right? So I'm going to hit Control-D for the end of file. So what do you think happened? Let's do the hex dump first. Let's do it the naive way first. Let's just cat this file, all right? Here's the command right there. Let's see what we got. Well, you just might argue, well, you didn't went backwards, you went forward, and it just put these at the end of the line, keeping the carriage return all along. It's fine. No, it isn't. Let's look what's really in that file. Remember, it ended here. Before we messed it up, this went from 0 to 50 in hex. And so there's 50, 51, and 52. That 0A was at the very end of the file, all right? So when we're done down here, here's the 50, here's this, and that OA right there, that end of line character, is where the end of the file was before we ruined it. Now we did a seek to the end of the file, which would put the current position right there. And then we said seek forward by 4. Well, 1, 2, 3, 4. Then we said write some stuff. All right? Well, there's the capital G. That's part of that word got. These zeros here are what the operating system does to fill in bytes that you never wrote into. So it's perfectly legal to seek past the end of a file and write off in Nowhereville. Okay? The operating system fixes it for you by adding these 4 nulls every time you try to seek 4 into the future and not have any data in there. So this is why you need to hex dump your files, all right? When you're developing code that seeks around and does stuff, you need to know, all right? Because you can't see this if you just print it on the screen. All right, so what about all this fun stuff in here? All right, well, the answer is sort of hiding in what really has to happen inside the software. And ultimately, the operating system on any Unix system is written in C. So the C++ library itself does nothing more than just forwards all the C++ stuff into the C-level operating system API. If I were to open this in append mode, for example, I wouldn't need to, go to the end of the file because I'm already in append mode. That might suggest to the naive viewer, that we simply are going to seek to the end of the file and not clobber the file. Because this goes back to this clobbering problem, right? How do you open a file without clobbering its contents? Well, one obvious way was just open it in append mode. We already seen that. Why am I going on about this? Well, append mode, if you what is it, 2 open. This is the section of the manual that talks about what the operating system literally does, okay? If you open a file and inside a C program, that ofstream class has to call open. It has to call this function, otherwise it cannot open a file, period. This is the only way to do it. Therefore, anything you do in C++ has to be translated into this. If you read in here, you'll see all these little flags in here. I don't need to go into all the details, but there's an append and some other details in here. Create the file if it doesn't exist. And you might recognize these other ones. There's a lot of things you can do you can't see that doesn't get expanded into C++. A time, no controlling TTY, no delay. Oh my gosh. So yeah, there's a lot of stuff in here, more than I remember. Temporary files, so and so on. Truncate the file. So you might recognize this, right? When we're opening for output, C++ always truncates the file. Well, it turns out this flag is on, is my point, when you call open for just an output file. Okay, that's why that happens. So, like I said, if you were a C programmer, you'd be familiar with this man page, and you would have known that there are all these flags in here. So you have more control at the lower level than you do in C++, is my point. So I have not read the actual C++ specification. It's 1,500 pages long. I've got other things to do this morning, so I didn't do that, but I suspect that by doing this, the C++ library API sets that append flag. All right, now while we're in here, let's look and see how this is documented. The file is open in append mode before each write. And this is the only way to write data into a file on a Unix operating system. Unix, Unix derived, Macintoshes, all these other, anything in the world these days other than Windows. And even Windows simulates this. The file offset is positioned to the end of the file as if with lseek, which is the actual operating system, super lower level, bottom of the layer. seekp calls that thing, okay? The modification of the file offset and the write operation are performed as a single atomic step. So what happens is, if you open it in append mode, every time you write anything to the file, it is as if somebody somewhere snuck in an extra call to seek to the end of the file, no matter what, okay? Now that should provide you some insights here as to what we can expect to happen. If I open it in append mode, it won't clobber my file, because that's the definition of what C++ tries to make happen if I open in append mode. It makes this thing pointless, but it makes this thing not accomplish anything. If I seek around in that file, and then later on I try to write data into the file, which is ultimately what happens when you use the insertion operator, and you write data into this file, it will reseek to the end of the file. So let's leave the code exactly the way we just saw it, and do this seek for, which should leave those empty nulls in the file. And let's see what happens. So what do we got? We already have some data sitting in this file. Let's see where we're at. I was messing around between takes. So it looks like that. Here's the hex dump of the file. And we can see it ends at 06, C. The next address is E. The way you read the hex dump here is that this address down here is the address of the byte after the last one shown. All right, so if this says 6E here, this must be D, because this would be the E column and the F column over here, all right? Anyway, my point is it ends with this OA, and you can see you got D, less than, and the end of line character right there. So if we run prog 5 now, and what are we going to do? We're going to say, make it obvious. Let's put a bunch of capital X's in here, and some Y's, and maybe some Z's, all right? All capitals. And we hit end of file by hitting Control D. Let's redo our hex dump, because we know we can't check anything unless we really look in here, because what it should have done at 6E, right, the end of this line, this was where the file ended before, and you can still see that right up here, 64630A. That's where it ended before. We seeked for into the future, past the end of the file, then we wrote, and lo and behold, it didn't work, because we're smart and we know that C is underlying the C++ API, and we read that lower level doc, and we inferred what app will do, and that is not clobber the file when we open it, which obviously was shown, but it doesn't allow us to seek around. It won't let us seek backwards either. Let's recompile, rerun again. Oops. And what we do now, a bunch of Q's and R's and S's, okay? And we write those in. We enter the file here. We do our hex dump. And you can then see again over here, here's the Z's that we saw before, the single carriage return, and so on. It's not backing up. It's not overriding those files. In fact, if we cat this file at this point, we can see none of these carriage returns were overwritten, and all the XYZs at the ends of these lines down here were not removed either. You could argue these are this data was from some other thing I was playing around with before I started the camera back up. Okay, so obviously append does not address our need is the whole point of this, right? So this non-intuitive thing over here is what you need to do if you really want to be able to seek around in a file without first clobbering the file. All right, let's take another big leap here. What do we got here? This time I'm actually going to create an F-stream. All right, so far we're talking about in streams and outs, and IF streams and OF streams, the input streams and output streams. Now I'm talking about just a file stream. I'm going to call my variable this time IO, because this is actually a stream that allows me to both input and output at the same time with the same file. All right, so this is what's new here. I'm going to use the same file we've been doing the whole time. When I open it, I'm going to do the same thing we did in the last program. Open it with both input and output. Okay. However, because it's an F stream instead of the O stream that we did in the last example, this really will let me read and write at the same time. Okay, I check to see if it opened up okay. I create a nice string variable for playing around with as a temporary for reading and writing strings. And what do I got here? See, this is seek G. Last time we were talking about seek P. This is seek G. Think of get. All right, the seek G has to do with I want to move around the file position, the pointer to the current position of the file for the subsequent commands that have to do with getting data out of the file. Okay? So what I'm going to do, I'm going to say seek G to 0 from the beginning of the file. That just rewinds the file. There's sometimes different languages have a command that actually says rewind, okay? And that goes way back in the old days because you would literally have files stored on tapes and they were literally rewinding the tapes. So if you ever see a comment about rewinding a file, that's where it comes from. And this is literally what it's doing inside there, okay? I'm going to then say tell G, just like we did before. I could tell G, just like I could tell P, all right? And we'll see that it says, oh, okay, I'm at position 0. And what do we got then? We're reading from, now notice I'm reading from IO. I'm reading from the file that I opened and rewound back to the beginning, all right? So what I'm going to do is I'm going to read the contents of the file, one string at a time. And there's all the stuff already in the file. Thank you very much. When that while loop ends, if you watch my other review lecture on what it means to read from a file, you'd know that the reason this works and the reason this while loop ends is because this expression is a Boolean value that represents whether or not the insertion has failed. Now, there's many reasons. Well, I can think of two immediately off my head, top of my head, why this could fail, right? It could be that there's some data in the file that it cannot read, given that the representation of this string. It turns out you can pretty much read anything in it with string. But if this was an integer or something like that, and the file had data in it that was not not a number, a digit or something like that, then that would be a failed assignment, a failed extraction, and failed type conversion in order to be stored in that variable. And it would put, my point is, it would put this stream object into a failed state. And we need to clear that failed state or nothing else will work down here, okay? We'll run it again in a minute, and I'll show you what happens if you don't put that in there. After that, we say, where am I? I'm at tell P. So I'm going to ask, I don't know where I'm at right now. I open this file, remember this object, this Ifstream object, this IO, and I said for input and output. And the way the API in C++ works is it has a separate notion of the position for reading, which is this getting, this G, the seek G, and a separate position for the P, the putting, the writing. Okay? So when I write my code, I treat these independently. You'll see they're kind of related, but I would strongly recommend that you treat them as though they're completely independent. In other words, we'll see that reading the file has moved around the writing position, okay? But I wouldn't bank on it. I suspect that's always the case, but the way the language is specified, do it as they intended, okay? Because something could change someday and then all your code breaks. So what we're going to do is going to clear that failed state that I know will exist. Then we're going to ask, where am I right now? In theory, it could be anywhere. So therefore, I want to add stuff to the end of the file, all right? So I'm going to seek P for putting, for the subsequent writing down here. I want to go to 0 bytes from the end of the file, all right? And for debugging, I print out where it is before and after I've done the seek P. Okay. Then I read from standard in, and this is the same loop we saw in the very first little program demo, where we just simply read a string and I print out here, I'm going to add this to the file, and then I write got whatever the heck and write that into the file itself. Because notice I'm writing into IO and not, C out or anything like that. When we're done with this, he reaches end of file, and the while loop ends, we close it, which will flush it, and we stop the program, okay? So let's go ahead and compile it. I guess it's already compiled. What are we going to do? Let's delete our file here that's full of nulls and other garbage data from the last thing that we did. Now let's do a touch on the file so we create an empty one, because this won't create me a file. It'll be like last time. So we need to create one. And we do a touch, and you can see here's my test file 2, and I have 0 bytes in it. All right, so let's go ahead and run program 6, which is the one we were just editing. And okay, so what did it do? Remember, it's going to print the current contents of that file out, one string at a time. And before it does that, it did the tell G. So it says, hey, I go to the beginning of the file. That's going to be 0. Now, when it's done, it goes to the end of the file. Current file is empty, therefore all these are 0. So we'll run it again and we'll see what happens. So let's go A, B, 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 C, 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 and it'll insert 3 of our little messages. Let's put an end of file in there and look see what happened. The file grew. Let's hex dump the file again. And we can see the got A, got B, got C, and at the end of each one, there's a new line. Right, the end of line byte, the OA. And there's no extra junk in there. There's no nulls. It didn't screw the thing up, okay? That's the key, right? Let's go ahead and cat it as well. Since it's correct, it will print out a couple of lines like we saw in the first little demonstration, okay? Now let's run it again. Jeez, I can't type. All right, now what's going on here? Remember, the first thing it does is it says, here's all the stuff already in the file. And it rewinds it, and it reads one string at a time. Now, because this is the file has got space this thing, got space this thing, and I'm reading strings from the file. Got is a string, and this thing is a string, right? So that's why you see got and the thing with the angle brackets around it and so on, okay? When it's done with all that, like I said, coincidentally, it updated the writing position, the seek P position, the tell P method tells us if we write into this file now, we would go at the end of the file. I then said, I don't care, seek to the end of the file anyway, in case we're not there for whatever reason, which didn't move it at all. So anyway, let's now write 111, 222, 333, 444, 555. Hit Control D. Let's go ahead and hex dump the new file out. Okay, so remember the first time it ran through, it had A's, B's, and C's, and that was the end of it. So here's our A's, B's, and C's in the hex dump file. This little dot here is the end of line character right there. So we went to the end of the file, and we wrote and got 1, 1, 1, 2, 3, 4, and 5, and so on. And there's the new line, the end of line characters again. So let's go ahead and cat this out so it's a little easier to read. And we can see we have now both read and written to the same file. Okay, so that's how you do that. If you open it as an Fstream and you say, I want both ins and outs. Okay, but if you do this, you need to keep your wits about where you are, and that's the whole point of this. I can ask where I am at. I can go to where I want to read. I can ask where I'm at for writing. Tell me where I am if I'm going to put something new in the file, or go here for the next time I want to write something into the file. Okay, and now it should be intuitively obvious that I'm not seek peeing all the time down here. So every time you write something into the file, it automatically moves that seek p to the end every time you put something new in the file. It does the same thing for the G, right? Every time you read something, you don't get the same thing over and over and over again. It's always doing the seek G. It's a natural part of, by default, every time you grab something from a file like this. Okay. All right. So as I promised, let's go back and look and see what happens if we don't clear the failed state from our file and we run it again. So here's prog 6. Can't create it. Okay. I removed it. Let's go ahead. Here's what we got. I forgot to do a touch. Start with a fresh data file here. So look what happened. Seek p position is -1. You know, WTF, right? Well, the file is empty, so there's nothing to read. We saw that before. Then we tried to seek to the end of the file. Now, the -1 means that the seek operation has failed, okay? That's coming from this line right here. That tell p, I should say, is the thing that actually failed, not the seek. This is the thing that reported the -1. Why? Well, you can't ask where you are for writing on a file that's in a failed state, okay? So if you leave this thing out, what'll happen is as you go along, all of these things will fail after that. Now, let's go ahead and add some more comments in our loop here, right? So let's say we add to the file, and let's go ahead and just print out, you know, tell p as I go, right? Let's see what happens. So A, B, 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 C, 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 -1, -1, -1, -1. Now, I honestly don't know if the writing is succeeding. I suspect it does not. The seek p or the tell p function is failing over and over and over again. Before we ran this, where were we? It was at, well, we ran it up here. I don't know how big the file was. It's still 0, in fact. This file has never had anything written into it at all. So the obvious answer is once you enter in a failed state, you can no longer tell p. You probably cannot seek p either. This returns a status as well that you could print out if you really wanted to. And all of these writing operations are failing, all because you entered into a failed state up here. And the only reason we entered into the failed state was because this extraction operator failed when it hit end of file, which is, as I explained before, the reason and the way, the method that this while loop knows it got to end of file and stopped running. So if you forget to clear your state, this is the telltale signs, right? You try to remember that, because someday this may very well happen. Now, this is not a very interesting application anyway. We can do other things. Let's go back and steal a line of code from number 5, just for the sake of completeness. You know, once we've done both reading and writing, at the moment this application only writes to the end of the file as if we're like in append mode or something. You can't tell the difference, right? Well, now, if I do this, I'm reading to the end of the file, one string at a time. I then seek for writing to the end of the file, and I've put back my back it up for thingy in here, right? Now, in order to do that, it would be nice not to make a giant mess, so let's put my XYZ back in here like we had in the prior program, so that when I back up 4 characters, we can recognize cleanly and clearly that we're backing over the end of line in the X, Y, and Z, and the next line would start being written like there, like we saw with the prior examples. And if I do this, I can cut and... That's what you get for copying code. You always fail. It never works. You have to rewrite it to suit your needs every time. Anyway, I should have just typed that in. Okay, here we go. I also put the clear back in, by the way. So that's why this is not failing right now. Okay, so ABC, DEF... GHI and JKL. Okay, end of file. Look in here. We've got data in our file. We can cat our file. It's doing the same thing it did for program 5. And if we hex dump this, we can see once again ABC and then got DEF, got blah, 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 blah. And it is... You know, we don't have nulls. It's not full of broken garbage data or anything like that. So let's run it again. Make sure that once again it all works. Now here's I'm reading, and I get the strings one at a time, just like we saw before. The string delimiter is a space. That's why these all come together in chunks. And my seek p, of course, now works because I remember to reset it and so on. Let's put some 111, 222, 333 in there like that. End of file. Hex dump this up. Clearly, this is working. My JKL and so on. Before it ended with JKL XYZ carriage return. And just like before, when we started, we were at the end of the file. We backed up 4 and we wrote over this. The 3C right there is this less than sign. All right, so that's why... We've got JKA less than got blah, 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 blah. Cat the file out, and we see what we expect. So, all right, that's what this is really the whole thing. From this, you can build up on all sorts of other things. I used text for these examples to make it easier to just, you know, write into the files and read data out. You would normally never seek around in a file and do this sort of thing with text. You certainly can. There's nothing wrong with that. But it's more likely that you would do this while writing binary values in the file and seeking around and getting binary values out of the file. That'll be a subject of another video. Thanks for watching. See you next time.